All right, let's look at this example. So we're going to look at the function f of x equal to x squared minus x on this closed interval from 0 to 2. And what we're going to do is we're going to, in the first part here, we're going to find the total area for this region between the curve and the x-axis. So we have our curve sketched right here. This is f of x. And we're looking in between 0, x equals 0, so this point right here, and x equals 2. So we have the right side of our region here. And so we have this, we want to find the total area of this shaded region. Now when we look at this, part of our curve is above the x-axis and part of it is below. So what we're going to do is we're going to find the intersection points. What x values, where does our function actually cross the x-axis? Now we have a graph here, so we can probably tell it's going to cross at x equals 0 and x equals 1. But if we didn't have that, how would we actually, algebraically, how would we actually figure that out? And we take our original function, x squared minus x, and we set it equal to 0. Because that's where our function is equal to 0, that's when it crosses the x-axis. And so you might need to factor. You can factor out an x here. And then each of these factors tells us an intersection point, x equals 0 and x equals 1. All right, so we could probably do that by just looking at the graph, but if we didn't have the graph, we could do it algebraically, probably with factoring, or maybe quadratic formula if we needed to. All right, so that's step one. Then we're going to do a little bit of a, kind of like a sign chart, to figure out where our function is above and where it's below the x-axis. All right, so we're interested on the closed interval from 0 to 2. And then on this interval, we plot all of our intersection points that we found. So we found at x equals 0, and then we also found at x equals 1. And so really what we have here is we have kind of two subintervals. We have this interval from 0 to 1, and then we have this interval over here from 1 to 2. And what we're going to do is we're going to figure out on each of these intervals whether our function is above the x-axis or below. Now we can look at our graph here. We have our graph, so we can just figure this out. On the interval from 0 to 1, if we look at our function, it's below the x-axis, so below. And then if we look in between 1 and 2 on this section, well, there our graph is above. If we didn't have this, if we didn't have the graph, the way you could figure this out is with test numbers. So you could say, use t equal to 1/2 for this interval here, plug it into the original function, you get 1/4 minus 1/2, which is negative 1/4, and the fact that this is negative tells us we're below. And if we wanted to test the other interval, pick a number somewhere in between 1 and 2, maybe like 3/2, plug it in, and if it's above, you should get positive. So you could have done, yeah, like we said, t equal to 3/2. And what you should find is that if you plug it in to the original function, it should be positive, which means above. All right, but we have our graph here, so you can clearly see in between 0 and 1 the graph is below, and in between 1 and 2 the graph is above the x-axis. All right, so we just want to keep that in mind. So what we're going to do is we're going to calculate, in the last step, we're going to calculate the areas. So to get the total area, we want the area that's above, and we want the area that's below. All right, so let's calculate. We're going to calculate two different definite integrals. We're going to do the integral from 0 to 1 of our function. So we're integrating our function x squared minus x, and we're just going to go from 0 to 1. So let's calculate this out. Antiderivative is 1/3 x cubed minus 1/2 x squared. We're going to evaluate this from 0 to 1. Top number goes in first, so we get 1/3 minus 1/2. Plug the bottom number in second, so we plug 0 in, we get 0. And this ends up being negative 1/6. Now what this represents, why is this negative? Well, this, if we're integrating from 0 to 1, the reason why it's negative is because in between 0 to 1, our function is below the x-axis. So that means the area below is 1/6. It's the negative of this integral. All right, so the area for this region below, we can integrate our definite integral, but we have to adjust for the fact that our function is below the x-axis. And the way we adjust for that is by putting another negative in front. So we end up with a double negative, and we make this positive essentially. All right, now let's try the other integral. So we're interested in this other section here from 1 to 2. So we're going to integrate from 1 to 2. Same function. So that means it has the same antiderivative, 1/3 x cubed minus 1/2 x squared. And we're going to be plugging in 1 to 2. Top number goes in first. So we get 8/3 minus 2. Bottom number goes in second. So we get 1/3 minus 1/2. And then we subtract. And if we clean this up, we can actually simplify this down. And what do we end up with? So, well, this ends up being a negative 1/6 here. And won't go through it all, but we end up with 5/6 if we simplify this down. And so the fact that we get a positive value here, the fact that we're getting a positive value here is reflected in the fact that our graph is, on the interval from 1 to 2, our graph is above the x-axis. So the area above on this interval from 1 to 2 is just our definite integral, the integral from 1 to 2 of x squared minus x dx, which we're saying is 5/6 if we were to simplify this down. All right, so we have our area below, it's 1/6. We have our area above, it's 5/6. And so to get the total area is just these two values added together. So the total area is equal to area below plus area above, which is 1/6 plus 5/6, which is 1. So the area for this entire shaded region, area for that region is 1. So it's always pretty remarkable that we can do these definite integrals and figure out what the area for the shaded region is. So the kind of the key process here, if we're trying to find the total area, we need to find these intersection points. We need to figure out the intervals where our function is below and above the x-axis. And that motivates us on what integrals we have to calculate. So integrating, why did we integrate from 0 to 1? Well, on that interval, our function was below. So we had to integrate from 0 to 1. Then, on the interval from 1 to 2, our function was above. So that's why we integrated from 1 to 2. And we had to do these separate, because if we were just going to integrate from 0 all the way to 2, what would we get? And that's what we're going to see next. If we were just to integrate from 0 all the way to 2 without making that distinction, without splitting up the integration and kind of adjusting for being above or below, that would give us the net area. So let's go through. We're going to calculate same function, same interval. We're going to calculate the net area. So the net area is just our regular definite integral. So it's the integral from 0 to 2 of our function. So x squared minus x. Get the antiderivative, same antiderivative as before, 1/3 x cubed minus 1/2 x squared. We're going to evaluate this whole thing from x equals 0 to x equals 2. Plug the top number in first, we get 8/3. Plug the bottom number in second, we get 2. Or plug the top number in first, we get 8/3 minus 2. And then plug the lower number in, we get 0 minus 0. So, I mean, we could write 0 minus 0, and then we subtract the difference. But we don't need to write that. And this ends up being, if we get a common denominator, we get 2/3. So our net area is 2/3. And so really what this represents, another way to calculate this, is this represents the area above the x-axis minus the area that sits below the x-axis. So what was the area for this region that was above? We found that before. Let's go back. So the area above was 5/6. So the area for this region was 5/6. What was the area that was below the x-axis? We also found that. So the area that was below was 1/6. So the area below was 1/6. And if we subtract, 5/6 minus 1/6 is 4/6, which is 2/3. So this is just another way to check it. We could calculate the net area directly by just doing the definite integral, but since we already had this area that was above and we already had the area that was below, if we do the subtraction, we get the same value. And so there's a fundamental difference here between the net area. The net area it's calculating the difference between, well, the area above the x-axis and the area below. So it's kind of giving you a measurement of where more of the region sits. If your net area is positive, well, then more of your region is above the x-axis. If the net area is negative, well, then more of your region sits below. And if your net area is 0, well, then the two regions balance each other out. And contrast that with the total area. This total area calculation, what we're doing is we're just kind of ignoring the, well, we're not ignoring, we're adjusting for the fact that if we integrate from 0 to 1, that function is negative. And so we end up with this negative value for our definite integral. And so to figure out the area, we had to make this adjustment. So the fact that our region was below, we threw in this extra negative. So the definite integral for sections of our graph where it's below the x-axis, the definite integral gives us a negative value. And so to get the area, we just have to kind of make it double negative. Well, we'll try a few more examples like this, just to kind of develop, practice these area calculations.